Okay, let's look at a problem here where we're going to find the derivative, but we're not just going to actually find the equation for the derivative, but we're also going to find the derivative, the value, at a specific point. So we've got a relationship x cubed y plus y cubed x equals 10, and we want to find dy dx at a specific value at the point 1, 2. Okay, so that means that we're going to need implicit differentiation to find our derivatives here, and we're going to take the derivative with respect to x of x cubed y plus the derivative with respect to x of y cubed x, and that has to equal the derivative with respect to x of 10. Okay, so both derivatives on the left side require the product rule, 1d2 plus 2d1. So we're going to do that step in our head. I've got 1, which is x cubed. The derivative of y with respect to x is dy dx, so there's 1d2 plus 2d1. The derivative of x cubed with respect to x is 3x squared. So there's the derivative of the first part. One step, one step. Okay, now we need the derivative of the second part, the second term on that left side. So we need 1d2 plus 2d1. Okay, and there's the derivative of the second term. 1, which is y cubed, times the derivative of the second function, the derivative of x is 1, plus the second function, which is x, times the derivative of the first with respect to x. So derivative of y cubed is 3y squared dy dx. Okay, and there's the derivative there. Now, that equals the derivative of 10 with respect to x. The derivative of a constant is 0. Okay, so we end up with x cubed dy dx plus 3x squared y plus y cubed plus 3xy squared dy dx, and that equals 0. For this problem, we are not asked to find dy dx specifically. We could, at this point now, solve it for dy dx, and we'll do that in a second. However, if you were just looking for dy dx at the specific point, I could plug in for x and y now, get all numbers except for the dy dx operator here, and solve for that. But let's just look at it more formally. Let's move everything that doesn't have a dy dx to the right, keep everything with the dy dx on the left, and we'll solve for it, and then we'll plug in the x and the y that was given to us. And again, that x and y better be on that original curve. So had they only given us an x, we still could have done the problem. Okay, so x cubed dy dx is on the left. 3xy squared dy dx is on the left. I moved the 3x squared y to the right, made it negative. Moved the y cubed to the right, made it negative. Now I'm going to factor out that dy dx. Left with the binomial x cubed plus 3xy squared. Not doing anything to the right side. Okay, lastly, I'm going to divide by this binomial to come up with an expression for dy dx. And again, that's the derivative of y with respect to x. Change in y over change in x. So I've got dy dx equals that right side, negative 3x squared y minus y cubed, divided by the binomial, which was acting as a coefficient for the operator dy dx. Now I have an expression for the slope of the tangent line at any value. Now this problem particularly said find dy dx at 1, 2. Okay, so I'm going to draw a line here, and then I'm going to say dy dx. I'm I'm going to do a vertical bar here, and I'm just going to put the ordered pair down here. That's going to tell the reader I'm finding dy dx at this ordered pair 1, 2, which means I'm going to plug in 1 for x, 2 for y into this expression. So I've got negative 3 times 1 squared, as I said, 1 is going in for x, 2 for y, times 2 minus y cubed, y was 2, so that's 2 cubed, divided by x cubed, 1 was x, that's cubed, plus 3 times 1, that was x, and y was 2. Okay, so there is the expression that we're looking for, and again, all numbers now on that right side. So I've got 1 squared is 1, times 2 is 2, times negative 3 is negative 6. 2 cubed is 8, so that's minus 8, divided by 1. 2 squared is 4, times 3 is 12, so 1 plus 12, or we end up with negative 14 divided by 13, and that is dy dx at the ordered pair 1, 2. So the slope of the tangent line at the point of tangency 1, 2 to this original function, x cubed y plus y cubed x equals 10 is negative 14 thirteenths. And if we wanted the whole equation, we would just put this into point slope equation. Here's your x, here's your y, here's your m, or here's your slope here. Okay, implicit differentiation to find the slope at an ordered pair.